Okay, good evening, everyone. My name is Varnit Kapoor, and let's start with tutorial for week number 8 today. So I'll be taking up your tutorial, and I'm pursuing my PhD from IIT Delhi. So I hope everyone is regular with their lecture videos and assignments, as it's very important. Repeatedly, I say in every lecture, right? So let us start. We last time we were discussing about structure and structure meshes for orthogonal. And today we will talk about unstructured, non-orthogonal meshes. Okay. All right, let us start for today then. Let me share my screen. Okay, the student has joined. Okay, so let me first share my screen. I hope my screen is visible for week 8. It's very important for all of you to be regular to your assignments and course content taught by the prof. I guess 2 students have joined, Rishabh Kumar and Sakshi Mangal. Okay. All right. Maybe others will also join with time. So let me start. And if you have any doubts at any point of time, please let me know. Stop me at that point of time. So topic is steady diffusion. On an unstructured non-orthogonal mesh. Unstructured non-orthogonal mesh. Okay. So last time we did orthogonal, unstructured. This time unstructured as well as non-orthogonal. So what do we mean by non-orthogonality is that the area vector is not parallel with the unit vector, okay, of that face. Suppose I have some unstructured mesh first of all, okay, and this is my area vector pointing. So one is towards this, okay, F, all right, and these are the cell centroids, E0 as well as C1. They're connected like this. So the line connecting is not parallel to the area vector. So that means we have or non-orthogonality. So E theta, let me write go. This is the these and this is not parallel at all. Okay? They are like quite likely to diverge. Okay? And C1 has the coordinate of x1 comma y1. C0 has a coordinate of x0 comma y. These are the points and one direction. This is E theta hat and this is E, you can say E eta hat. So this angle is not 90 degrees. Not. All right. Suppose this point is point A, this point is point B. And this is your face. This is your face. Your current coordinate system is, this was your orthogonal coordinate system, the universal coordinate system I hat, J hat. Okay. All right. And let us make, so the silhouette here is, this is in the direction of eta. So this is delta eta. Okay. And will be delta zeta. That will be, this is your direction for delta zeta. Delta zeta. Okay. This is your delta zeta. All right. Also, this area vector is pointing in some direction. So it will be having two components. One is in the x direction, one is in the y direction. Let's, this area vector, this area will have two directions. Let me make with the green color. Okay. So one is an AX. This is AX. And this is AY. Okay. AY. So AX doesn't mean AX like this. Okay. It's the X in the direction of X. This phase is being decomposed. And in the direction of Y, the phase is being decomposed. All right. So if you say in a uniform grid, structured grid, you say that this is X direction and this phase is AX. Okay, whereas if I make it as 2D now, if I make it as 2D or 3D, suppose I make it as 3D. So this is the X direction. So area corresponding to this is AX. This is the Y direction. So the area corresponding to this is AY. Okay, in Y direction. This is your Z direction. The area corresponding to this is AZ. Correct? Okay. So that is what I've taken. I hope that much is clear. Okay. Now let us start the discretization of the equation. First, we will write the diffusion equation. What is our diffusion equation? Del dot gamma grad phi plus if there is any source term is equal to 0. We are using FVM. As you all know, course name is FVM only. So we'll do summation. The steps are same. Gamma grad phi of faces dot after GDT and everything I'm doing directly writing. Okay. Dot product of this and source term del V equal to 0. Okay. Now this time the area vector is decomposed into two directions. Area vector AF is decomposed AX in I hat direction and AY in J hat direction. Okay. Similarly, how you will write the gamma grad phi term, okay, of that phase, that will be decomposed for that phase plus in the I hat J hat. I hat J hat. First, let us write like this. So I rho phi by dou x is J rho phi by dou y of that particular phase, whatever phase you are taking. Okay. All right. I hope this much is same. Still here, clear. If you have any doubts, please ask. Okay. So what we have done, we have discretized the gamma grad phi as a written as grad phi can be written as I dou phi by dou x plus j dou phi by dou y on the phase f F, right, which is shared between C0 and C1 cells. C0 and C1 cells. But what is the difficulty we are having in these derivatives is dou phi by dou x and dou phi by dou y, which cannot be directly calculated because phi values are not stored in the x and y direction. They are stored in an unstructured way because we have designed our system to be unstructured way all over the place. So that means basically phi values are only stored at the cell centroids. Okay, the cell centroid C0, C1 here. And these cell centroids do not align themselves along the direction of x and y. That is why we have taken E eta. We have taken this E eta direction and E eta, right? Okay. So do not align themselves in these directions x and y. We cannot work with dou phi by dou x, dou phi by dou y because phi values are stored only at the cell center. So if we can calculate the gradient in the zeta direction, that is a better way to work with because zeta direction is the kind of connected with C0, C1. The C0, C1 is connected in zeta direction where we have the values. Okay, because the mesh is not orthogonal. Okay, so how I can write the gradient? How I can write the gradient? Let us see how we will write the gradient now. So we can write, suppose if I'm trying to write gamma f e at theta dou phi by dou zeta plus e eta hat dou phi by dou eta. And that phase. All right, at that phase. Can I write like this? No, I cannot write like this because this is not an orthogonal system. It cannot be directly written like that as a dou phi by dou x, dou phi by dou y. So this is not equal to this. All right, this is wrong. So we cannot work with this. So because eta and zeta is not an orthogonal coordinate, they have an angle which is greater than this is e eta direction and this is e zeta direction, which is greater than 90 degrees. All right, than 90 degrees as defined by us. Okay, so we cannot see the partial derivatives dou phi by dou x, dou phi by dou y cannot be related to these other gradients. We need to look at to the relation between dou phi by dou x and these two derivatives, dou phi by dou eta and dou phi by dou zeta. In order to do that, we will recall that phi as I want to calculate dou phi by dou zeta, where phi is a function of both x and y. So how I can write dou phi by dou zeta? If I want to write dou phi by dou zeta, how I will write? I will write as a partial derivative of x and x as a partial derivative of theta plus dou phi by dou y plus dou y by dou how much? Theta. Okay. Can I write like this? Yes. We can write this as a phi, which is indicated as the gradient dou phi by dou zeta, and this can also be written as phi of theta. This means it is a gradient of phi. Okay. This is a gradient of phi. All right, because mesh is not orthogonal. Then mesh is non-orthogonal, right? Mesh is non-orthogonal. Okay. I hope it is clear. Similarly, I can write dou phi by dou eta. That is dou phi by dou x by dou eta plus dou phi by dou y by dou eta. Now I can write this phi of theta. Okay. Now we have these two equations, equation 1, equation 2. I'll apply an operation. 1 into y of eta minus 2 into y of theta. Okay. Let us see what will happen. I'm trying to eliminate Which term? So y of eta is nothing but this is y of eta and y of zeta. This is y of eta and this is y of eta. Right? I'm trying to eliminate the second term. Let us see. So what I'm going to get? Phi of zeta, phi of eta minus phi of eta and y of zeta is equal to phi of x into x of eta. X of eta is this. This is x of eta, zeta, sorry. And this is x of eta, x of eta. So x of zeta y of eta minus x of eta y of zeta. So I can take out phi of x separately. This phi of x. Phi of x is nothing but phi of zeta y of eta minus phi of eta y of zeta upon x of zeta y of eta minus x of eta y of zeta. All right. Please correct me if I'm wrong at any step. All right. We have got this. Now, similarly, what we will do, we will again apply one more operation. So we have got phi of x. That is nothing but dou phi by dou x. So you got in this equation dou phi by dou x. All right. Now we will apply one more operation, that is first equation into x of eta minus second operation into x of theta. Again, first term we are going to eliminate this time. So that is phi of zeta x of eta minus phi of eta x of zeta is equal to phi of phi into y of zeta x of eta minus x of zeta y of eta. So here we will take out phi of y, this phi of y. This is phi of eta x of zeta minus phi of zeta x of eta over x of zeta y of eta minus x of eta y of zeta. This is nothing but dou phi by how much? Dou y. Okay. So we've got this dou phi by dou x, dou phi by dou y. These two terms you have got this term, dou phi by dou x and dou phi by dou y. You've got these terms. All right. Now, what is Jacobian? We have already studied in mathematics. Jacobian is nothing but this denominator term. This is x of zeta y of eta minus x of eta y of this is your Jacobian. All right. Okay. So now how can I write Jacobian equal to J? Let us denote Jacobian by J. So how I can write your expression that was gamma grad phi of that phase dot A of that phase. So you have gamma grad phi is nothing but I hat dou phi by dou x plus j hat dou phi by dou y, correct? Dot I ax plus j ay. All right. Okay. We have somehow related all these things, phi x, phi y, in terms of phi zeta and phi eta. No. Okay. So we have kind of related them. We have dou phi by dou x, dou phi by dou y. And we can substitute into the gamma grad phi. That is the original expression we want to evaluate. Okay. All right. Any doubts in this? In here, if you have any doubts, please ask Vishal, Sakshi. You can unmute yourself and ask. If you have any doubts, please ask. She's writing. No doubts. Okay. All right. No doubts. Great. Okay. I guess we have no doubts. We have no doubts. Pretty simple mathematics we are doing. Right. So let us put the values back. So what is dou phi by dou x gamma f? Dou phi by dou x is how much? This is your dou phi by dou x. Phi zeta y eta. All right. Minus phi eta y zeta upon Jacobian. So make sure that this dot is done with this, I with I, and j with j. All right. Let us do. So dou phi by dou x is how much? Phi theta y eta minus phi eta y zeta upon Jacobian into ax. All right. Plus what is dou phi by dou f? Phi eta x zeta minus phi zeta x eta upon Jacobian into ay of that phase into phase. All right. And if you do the dot product, multiply them after doing the dot product, you are going to get this only. Okay. Any doubts? No doubts. Okay. And expand again. So we have ax y eta minus ay. I'm rearranging all the terms to get the phi of zeta all together and phi of eta all together. Okay. Ax y eta minus ay x eta over Jacobian, that is dou phi by dou zeta. All right. That phase plus sum of that phase into ay x zeta minus ax y zeta upon Jacobian. Let me write it next time. This gamma f ay x zeta minus ax y zeta over Jacobian into dou phi by dou eta of that particular phase. So this is sum of this. Right in here, no problem. Pretty simple. Now question is, what is x zeta y zeta? What is x zeta y zeta? Question is this one. We have to find this. It is nothing but x zeta is nothing but dou x by dou zeta. Okay. So if you are going to calculate, how would I have calculated dou x by dou zeta? X1 minus x0, because zeta direction is nothing but joining C0 and C1. This is your zeta direction, E zeta hat. So it has a coordinate x1, it has a coordinate x0, y1, y0. Okay, x1 minus x0 over. This was your del zeta that we have made in the diagram. Okay. So how you will write x zeta? Okay. So x zeta which is dou x by dou zeta is nothing but x1 minus x naught over del theta. You observe the diagram I've already made. This is x1 point, this is x naught point, and this is your del theta. Let's go below. Okay. And what will be your y zeta? Similarly, y zeta will be rho y by rho zeta, that is y1 minus y naught over del zeta. Similarly, x eta pointing in the other direction. Rho x by rho eta, that will be how much? Now this time, eta is pointing in A and B direction. So self this direction, A and B. So eta is in this direction. So how I will write? X of B minus x of A over del eta. And I should write like this, xb minus x over del eta, and y of eta will be rho y by rho eta, that is y of B minus y of A over del of eta. Del of eta. Okay. I hope it is clear to you. So we have set up all the things. There's our matrix for all the coordinates. It's quite simple, 0 and 1 and A and B, right? 0, 1 pointing in zeta direction, A and B pointing in eta direction. We have these 4 coordinates which we are calculating the methods. Now what about AX and AY? So how you will get AX and AY? So AX we have identified as the length in the Y direction. If you remember, this was your AF. It decomposed here initially. This is your AX in the Y direction and AY in the X direction. Okay. All right. This is the projection of the face area vector onto the Y axis and X axis. Right. So how we can write AX and AY? So AX can be written as, this is YB minus YA, and AY can be written as X, how much? AY XA minus X. Okay. Because this point has coordinates. This point has coordinate XA, YA. This is your, suppose B point, XB, YB. This was your B point, which has coordinate XB, YB, and this was your A point, XA, YA. Right? You have made the projection in X direction and Y direction. All right. Let us write the area vectors. AX will be how much? YB minus YA, and AY will be how much? XA minus XB. Now the area vector was written as I hat AX plus J hat AY. So I hat AX is YB minus YA plus J hat is XB minus XA. Okay. So you got AF, which has AX and Y hat as well. So you got all these terms, X hat, X zeta, Y zeta, as well as AY, AX, you got, and Y eta, X zeta. All these terms you have gotten. Now question is, what will be E zeta? E zeta is nothing but a unit vector. E zeta is a unit vector. That is nothing but zeta is pointing in 1 and 0 direction. Unit vector is nothing but vector over its magnitude. So in the zeta direction, this was your C naught, this was your C1, this was your E zeta. Vector can be written as I hat. These are the coordinates x1, y1, and x naught, y naught. Right? So x1 minus x naught j hat y1 minus y0 over magnitude of this. That is x1 minus x0 whole square plus y1 minus y0 whole square. This is your theta direction. That is nothing but this is your delta zeta. This was your delta zeta only. This was in the diagram, okay, which you made above. So that is I x1 minus x0 plus j hat y1 minus y0 over del of zeta. This is your e zeta hat. Okay. Similarly, you can write e eta hat as well. I guess same procedure. This time xb xa e eta hat. So that is I hat xb minus xa plus j hat yb minus ya over del of eta. We got the unit vectors as well. Now, what was our Jacobian, which you are writing in the denominator? The Jacobian was written as x beta y eta minus x eta y zeta, right? You have x zeta y eta. You have already calculated above. That was x1 minus x0 over del zeta into yb minus ya over del eta minus xb minus xa over del eta into y1 minus y0 over del zeta. So if you rearrange and write it in a compact form, that can be written as EF dot E zeta over del eta. All this has been taught by the prof. So just giving a brief of everything. All right, it is clear. So this is your Jacobian. This is your Jacobian. Still here, any doubts? Risha, do you have any doubt? Please unmute yourself. You can unmute and speak. Okay, no sir. All right, no doubts. Pretty simple. Okay, now we had one term that was axy theta minus ay x theta. This term. So we have calculated the Jacobian. We've got we have to see this term ax y theta minus ay x theta. Okay, of this dot product. Let us see. We had one term that was ax y eta minus ay x eta equal to what is ax? We have already calculated ax. This is your ax yb minus y and y eta also you have calculated y eta divided. Okay. This y eta you have already got no above. So that is yb minus ya into yb minus ya over del eta minus what is ay? Ay also you have got as xa minus xb into xb minus xa over del eta. Okay. Oh, sorry. If I'm writing both xa first, so it will be xp. Okay. So this is yb minus ya whole square plus xa minus xb whole square over del eta. So if you see, this is nothing but af dot af over del eta. You know what is af? Already we know that what is it. Okay, I hope it is clear till here. And another term was ax y eta. Okay, so this whole term was written as this over Jacobian. Okay, so we will put this Jacobian here now. So let us put. Therefore, ax y eta minus ay eta over Jacobian. This can be written as af dot af over del eta upon Jacobian as af dot e zeta on del eta. So this and this term cancels out. You are left with af dot af over af dot e zeta e zeta. Okay. Similarly, there was one other term, ay x zeta. This term, ay x zeta minus. We have done this term completely. There is a second term as well. Okay. Where is it? Yeah, this term. All right. So let us write that term as well. Ay x zeta minus ax y zeta. So you know all the terms. This is xa minus xb into xa minus xb over L theta. Okay. Minus yb minus ya into iv minus ya over del theta. So this can be written as, again, I made a mistake. X zeta. Oh, sorry. X zeta is not pointing in the direction. So x zeta is x1 minus x0. Ay is in the xa minus xb. Okay, you are seeing, but x zeta is between the centroids, x1 minus x0. Similarly, y1 minus y0. Okay, all right. Okay, so this is nothing but minus sign if you take out yb minus ya into y1 minus y0 plus xb minus xa into x1 minus x0 over L zeta. This can also be written as, if you simplify e zeta dot en to L zeta. Okay. Now again, you will divide by what? Jacobian. Let's divide by Jacobian. So ay x zeta minus ax y zeta over Jacobian can be written as minus e zeta dot e eta del eta, and Jacobian is nothing but af dot e zeta over del eta. This is minus del eta square. This time they are not cancelling out. If you observe, e zeta dot e eta over af dot e zeta. Af dot e zeta. And this term can again be written as af dot af over af dot e zeta into e zeta dot e zeta with a negative sign. All right. Okay. I hope this much is clear. So now you put all the values all together, all the values which you have calculated in that equation. Therefore, we can say that our equation was gamma grad phi of that base dot EF was, put all these values, the first term and the second term. That will be gamma F. First term is AF dot AF dot E zeta into Rho phi by rho zeta of that phase plus, sorry, minus gamma f af dot af over af dot e zeta into e zeta dot e eta into dou forward dou eta of that phase. So what we can say, we have two gradients this time, if you observe. We have done for a particular phase first time, like suppose east phase. So this is something different from what we have been doing. Till now, we used to have one derivative coming at each and every phase. This is for one phase we have done so far. Only the phase which is connecting C0 and C1. The phase which was connecting this phase here. Okay. We used to have only one derivative always. For a east phase, suppose in the structured mesh, how you used to have gamma A dou phi by dou x of east. And for the west phase, you would like dou phi by dou x gamma A into dou phi dou y of west. Only one derivative used to be. But here two derivatives are used. Coming. This one, zeta and eta. Okay. Okay. So if you are talking about east phase, you got dou phi by dou x, right? And if you are talking about north phase, dou phi by dou y, as I said. But in the context of unstructured orthogonal meshes, we only have one quantity, dou phi by dou zeta. But we have unstructured orthogonal, but this is unstructured non-ortho. So we have dou phi by dou zeta as well as dou phi by dou eta, dou phi by dou zeta and dou phi by dou eta. Okay? That is a manifestation. So non-orthogonal of the mesh, because of the non-orthogonal of the mesh, we call the first one, which is the first gradient, we call as a primary gradient. This gradient is called as primary gradient. And this gradient is called as secondary gradient. All the hard work for getting this dot product of this. Okay. I hope no doubt still there. We have got the gamma graph. We have got the two gradients, that is primary gradient and secondary gradient. Okay. Now question is how you will get phi of zeta, that is dou phi by dou zeta, this term phi of zeta, and phi of eta, that is dou phi by dou eta. Is the question. We have not got this so far. Let us think for 2-3 minutes. I'll get back to you guys. Okay. If you guys have thought, let us proceed further. Now to get the values of phi zeta and phi eta. Phi of zeta is nothing but dou phi by dou zeta at that phase is okay. As well as in millimeters how much? By linear profile assumption, phi 1, well, your zeta is connected with 1 and 0, C1 and C0 minus del zeta. Okay. And suppose we assume that this whole term to be SGF. We say it as a this term is called as SG secondary gradient at phase. We call this like this. And here we have applied linear profile assumption. Okay. In zeta direction, that is phi 1 minus phi naught upon del zeta. Right? Phi 1 minus phi naught upon del zeta for the phases. That is what we have. We have the stored values of at the cell centroid. And you have to note this that del zeta for that phase needs to be there because del zeta would be different for different phases. And depending on the cells we are connecting. And let us talk about the secondary gradient. As of now, we would leave it like this only, as I've said, SGA. So how I can write the complete term as gamma, this whole term gamma at phi phase dot A of F can be written as gamma F over F of that phase into AF dot AF over AF dot E zeta into x1, sorry, phi 1 minus phi 1 minus phi naught. This is zeta I've written here. Plus your secondary term is G of secondary gradient. Now, if it could have been an orthogonal mesh, we would only left with primary gradient. There won't be. Okay. If it would have been an orthogonal mesh, what would have happened? Think once again. Then how I can write AF dot AF? First of all, you tell me like this. AF dot E zeta can be written as AF square over AF magnitude is equal to nothing but AF. Okay. I can write like this, right? Which is your primary gradient, the term from the primary gradient. So which we have replaced with the linear profile assumption here. Okay. Phi 1 minus phi naught over del zeta. So when you have done it as an orthogonal mesh, the formula would have to revert back to the right expression corresponding to this orthogonal mesh. Okay. So gamma f AF by E del zeta F can be written like this. So for the orthogonal mesh, the primary gradient coefficient will revert back to the correct expression, and secondary gradient will become to 0. Because if they are orthogonal, suppose if they are orthogonal, then zeta and eta will be in 90 degrees angle. Okay, this will become 0. So you will be having only the first primary gradient, which we have like this. Okay, and secondary gradient will be written as SGF can be written as minus gamma f AF dot AF over AF E zeta into E zeta dot E eta phi of f that phase. This term will become 0 for orthogonal mesh. All right. So here the secondary gradient is, so for the orthogonal meshes, primary coefficients or the primary gradient coefficient will revert back to the correct expression, okay, to that of the orthogonal mesh. And the secondary gradient will become 0 because secondary gradient is nothing but minus of this, and the dot product is coming out to be 0 as they are orthogonal. And here, if you say the secondary gradient is being problematic only, so for primary gradient, dou phi by dou zeta, we have the cell centroid values, that is phi 1 and phi naught, and we could compute it directly. Whereas for dou phi by dou eta, this term, we don't have directly. We can name this, let us say, some A or B. Okay. So B minus A, phi B minus phi B, phi A. If we want to calculate this dou phi by dou eta, we somehow need to calculate phi at these vertices. Okay. The vertices A and B. But this data is not directly stored right. That is not something we solved for. So how you will calculate phi A and phi B? Using interpolation, you can write phi B minus phi A by del eta. You have several cells using all the cell centroid. You can somehow calculate phi and phi B. And use these values to calculate what is partial phi by partial eta. Now, if you see, it takes out the term, what can we do in the context of two-dimensional problems? Okay, so SGF is a problematic thing currently. Problematic because directly we don't know the value stored at the vertices A and B. Now let's come to the two-dimensional structured mesh. Two-dimensional structure. Let me write the heading. So we have a 2D structured mesh. Suppose like this we have. Okay. This is a cell centered C naught C1. Okay. This is your vertices B, A, where theta values are constant, of course. Okay. And here eta values are constant. If we have this 2D structured mesh, we are talking about two-dimensional curvilinear mesh, which could probably something look like this. So we are talking about a mesh like where we have maybe some zeta equal to constant and eta equal to constant lines as I've made, which will define ourselves. And this is some kind of curvilinear coordinate. And these are our C0, C1 for east and west and so on. And we are interested in calculating what is the gradient on this face. Okay. All right, the space F. In this direction. So this is our eta direction, basically. Okay. Let me write the zeta equal to constant as I've written here. That changes the thing. So zeta equal to constant, let us call that this is a eta equal to constant, eta equal to constant, eta equal to constant. Okay, these are the lines which make the curvilinear mesh. So using these centroid values, cell centroid values, we can calculate the values at B and A. So using the cell centroid values of here, of C0, C1, here and here, those. We can calculate the values somehow. Okay, from here also, and from here also. So using all these centroid values, we can calculate the value of phi A, phi B, and phi N calculated using the cell centroid by using this interpolation if you do. Okay. Of course, you can say dou phi by dou eta on a particular phase F. This is the expression of the secondary gradient can be calculated from phi B and phi A. Okay. So phi B minus phi A upon del eta can be written like this. Phi B minus phi upon phi eta on that particular phase can be calculated. Or if you do not have to calculate in this way, it can also be calculated like what is the gradient at the cell centroids. Okay, instead of interpolating the phi. So either you do dou phi by dou eta at a particular phase. Suppose, let me write. You can either write dou phi by dou eta at a particular phase. Either you can write phi b minus phi a over L of eta for that particular phase. Phi b minus phi over del eta. This is del eta direction. Okay. Or you can calculate the gradient at the cell centroid itself. Instead of interpolating phi, you can calculate dou phi by dou eta at cell centroid C0. And you can also calculate what is dou phi by eta at cell centroid C1. And then interpolate these two to obtain the dou phi by dou eta on that particular phase between these two cells. So either you can calculate the dependent variable at A and B and calculate the gradient, or you directly calculate the gradient at the cell centroid and then interpolate them on the phase. Either of the method can be used to calculate this. So what do I mean? First way is this. Second way is you can get dou phi by dou eta at the cell centroid C0 and dou phi by dou eta at cell centroid C1 and then interpolate. Now you interpolate to get dou phi by dou eta at that phase. Any doubts? So you get the values of dou phi by dou zeta from this node to get dou phi by dou zeta at this C0, and from here to here at C1, and then you interpolate between them. Okay. I hope it is clear. Now this was 2D structured mesh. Suppose you have a 2D unstructured mesh. Structured mesh. You have 2D structured, 2D unstructured. So let me make some mesh. Hmm. somewhat like this. Some unstructuredness is there. And this is your cell C0, suppose. This is your C1. Okay. Then all other neighboring cell centers, centroids. Okay. This is your phase under concentration F. Okay. Pointing in eta direction. Yes, I didn't make the eta direction. Eta direction. Okay. And this is your point B. This is your point A. Back again. For the 2D unstructured mesh we are talking about. So how to calculate this quantity at the cell centered again, dou phi by dou eta at that phase? Again, we have the challenge here. So we can calculate dou phi by dou eta at C naught. One thing is that how I calculate. We need to know the north and south values here for the C naught. So one way is to basically calculate dou phi by dou eta here and then average both of them and some kind of interpolation. So on north phase you would use let me like say number, you can number all the sin centroid 1, 2, 3, 4, 5. Okay. So you will get the values of dou phi by dou eta at north phase, which is coming off C naught, and similarly for the south phase and some neighboring cells, you can say. Yeah, and on the south phase as well. Suppose for the C naught, this is your C naught, this is your north phase, this is your south phase. Suppose, if I'm saying, the value will come from here and here. Okay. So for north phase, value will come from here. For south phase, value will come from here with some kind of interpolations. Okay. You got it on on these faces, and then you can interpolate between this and this same procedure. If you get from the north and south faces or the neighboring faces, you get the same procedure and then apply the interpolation. So there are several methods. We are not going to go into this thing. How we calculate the cell values. If we have a 2D unstructured mesh, we have triangular faces like this. We started off with some values. We have some triangular mesh, so I can write similarly like a strategy. Suppose how I can write this dou phi by dou eta at that phase can be written as phi at p minus 1 way is this at del of eta. Again, these are the values from the previous. So this can I write star values? First you have to assume the values, right? And interpolate to get phi and phi b's. As I said, interpolate phi and phi b is calculated from the north neighboring terms again. So we have C0 and C1, these cells centroid. We can apply interpolation method, engineering method for this unstructured meshes. All right, this has been already discussed by the prof also in detail. So I'm just giving you a brief here. And similarly, if you go for the 3D structured meshes, how it will be something kind of uh, tetragonal kind of a geometry you can make. So just give me a minute, guys. Okay, let's come back. So I was talking about 3D structured mesh. Okay. So we have some kind of a quadrilateral. Okay. If we draw, so suppose we have a kind of quadrilateral like this in 3 dimensionals. Suppose like this, we have. Okay. So it can be orthogonal, non-orthogonal. So we have a 3D structured mesh. There's some kind of quadrilateral we are talking about as we are talking about the structured mesh. And we have something like a cuboid kind of cells if you observe. So we have cell centroids as well, and this is connecting all the other cell centroids as well here. Suppose this is a cell centroid for this. It is being connected with some another here, cell centroid one, neighbor to it. Okay. So this is aligned with, suppose beta is equal to, this is aligned with beta is equal to constant. Okay. And suppose these are the coordinates with A and B, and these are the coordinates with C and D. So until now we have eta, which is along the face, which is along the face. in this direction, we have eta along the face. And in this direction, because it's three-dimensional now, it will have, we have zeta, we have eta, we have, we can take a third direction as well. So we have zeta along the phase, eta along the phase, zeta along the direction of, you say, joining C0 and C1. Suppose you can take some direction xi, third direction you can take. So this will be, this is a xi, third direction. All right. Perpendicular to the eta. And so it is not always necessary to be perpendicular. So far we had only A and B coordinates. We have two more coordinates, C and D. So in total, four vertices we have, A, B, C, D. So where these eta and xi need to be calculated. Eta and xi. So if we have to write gamma grad phi dot AF in 3D structured mesh, the gradients will look like you have three term system. Earlier we had two terms, primary gradient, secondary gradient. But here, one more gradient will come. Okay. Dou phi by dou zeta, dou phi by dou eta, dou phi by dou xi. Three terms will come. So we have primary direction. Okay. In 2D, we used to have primary and secondary. Here, one more direction will come. And you can say that it can be orthogonal as well, non-orthogonal. Okay. So it will have these secondary gradients. Two secondary terms will be non-zero. So total, we have three gradient terms. If we say we can boil it to like three-dimensional Cartesian mesh, we used to have dou phi by dou x, dou phi by dou y, dou phi by dou z. But there, ax is only pointing in I direction. And d phi by d zeta, d phi by dy and d phi by dz would come to zero that time. But here it is not. Okay. All right. So how I can write the terms here? So we have dou phi by dou theta at that phase, which can be written as by interpolation phi1 minus phi naught because it is being connected between C0 and C1 cell. So zeta. Okay. Then we will also have dou phi by dou eta at that phase. We will also have dou phi by dou xi at that phase. These two are the secondary gradients. In case of non-orthogonal, it's non-orthogonal. And we have this time phi A, phi B, phi C, and phi D. The primary gradient, we have secondary gradients. Now we come to three-dimensional unstructured. So you can solve what have been discussed. Three-dimensional unstructured mesh. 1D we have done, 2D we have done, 3D structured we have done, unstructured we are going to. So the unstructured mesh then means we can have some tetrahedron kind of symmetry. Difficult to visualize sometimes. And difficult to draw into 2D plane also. Okay. So it's pointed upward. Few of them. Suppose it has a cell centered somewhere here, C0, and it is connected with C1. Again, this is your zeta direction. Okay. Zeta, right? So it's a tetrahedron basically. And we have cell centroid somewhere, C0, connecting to another cell centroid C1, talking about one particular phase that happens. All right. So suppose this one is that. Okay. All right. So it's difficult to visualize on mine, which I have highlighted like this. Okay. So we are talking about right out of the tetrahedron. You can calculate the partial phi, the second gradient in the context as well. There will be three sides. So essentially what we have to do this, we call this some xi direction. We would end up with two different directions, which is basically you call eta and zeta and xi, which is a primary. And there are secondary directions as well. Again, you have primary and secondary gradients going to come. Okay. Because we have three x's, we are doing a three-dimensional case in the unstructured mesh. So essentially we have dou phi by dou eta on a particular phase, dou phi by dou phi by dou xi. Okay. And up till now, we could easily calculate them because either the eta direction is aligned with the phase direction. We would have calculated what is A and B, and then in the context of 2D as well. So similarly, in the context of 3D, we have some structured mesh. We could identify the phase by splitting it along the two sides, A, B, C, D, 4 points. We can interpolate and calculate. And the two directions, where would they lie? So lie in the plane of the face, right? On the triangular face, you need to identify these two directions to be orthogonal or non-orthogonal. So we can pick any two direction infinitely. Yeah. So I've drawn these two directions, this direction, this direction. You can take any two directions in any way. Okay, for this n-sided polygon. So it means that we don't have any consistency of picking in the way of picking something. That means there are infinitely possible ways where you can pick the directions of eta and zeta. Right. So we have devised something only for tetrahedral meshes. For example, you can say why cannot we connect this vertex with this direction and this vertex with this direction, which I've drawn. You can pick. I can connect any of these two, and we have another third direction with this for zeta. Suppose. So idea is like you will not work if you have something called as a pentagonal face or octagonal face. If you have something called a polyhedral cell or something like honeycomb structure, you can have many of you can have basically the face which will not be an insided polygon in general. Okay. Basically, the point is you can choose any two directions of your choice in any alignment. There are infinitely many ways to pick up this the two directions for this insided polygon. Okay. Again, you have direction zeta, you have eta, and something called psi. Okay, so this is your primary again, and this is your secondary. SG, secondary gradient and primary gradient. All right. And again, you need to calculate here dou phi by dou eta at that phase and dou phi by dou xi at that phase for this insided polygon. Insided polygon. A quite complex kind of thing you can explore on your own as well. And you can pick infinitely many ways. You can pick for eta and theta for the phase. You can choose any particular way out of that and solve. Now, how you will calculate? Let's come to the calculation of secondary gradient, which we wrote directly as SGF. Okay, let's come to that. Back to that calculation of secondary gradient. Let's come to this. Just give me a minute. Okay, so we had the equation that was gamma grad phi of that phase dot AF. So we had the primary gradient written as gamma F over del zeta F into AF dot E zeta phi 1 minus phi naught after linear interpolation, and we wrote directly SGF for the secondary gradient. Okay. Right. Any doubts? No doubts? Now, how you will write the secondary gradient? Your secondary gradient was nothing but minus AF dot AF dot E zeta into E zeta dot E eta. We have already written that. Do have a do n do eta of that phase. So this can also be written like this. Gamma F grad phi of that phase. What I'm doing basically, I'm subtracting this and this to get this. Okay, that is what I'm doing. F dot AF minus this is a total value and gamma F zeta AF dot AF dot E zeta gradient of F dot E zeta del zeta. Okay, so this was your total gradient, total value. This was your primary. So that is your SGF, secondary gradient. Okay. The question is how you will calculate this gradient of F. So we have transformed our problem of secondary gradient into calculation of gradient of phi, okay, on the particular phase. How can we calculate this gradient? This is where what is grad phi is asking about that which scheme you will use to calculate and why does it we have to calculate for use in secondary gradient. So one reason is that it is also used in many other contexts you will see for computation of gradient of phi's using the computers. Okay. So if you have an unstructured orthogonal mesh for the calculation of gradient, secondary gradient, how you will go ahead. If you use some CFD software, it will directly ask you what is the gradient calculation scheme, basically. How, or some kind of, you can say, should I calculate this gradient? Some kind of input will be there to put there. Okay. So if you have a calculation of secondary gradient for an unstructured non-orthogonal mesh, it is a good idea to make use of this structure and calculate secondary gradient from A, B, or ABCD values. Put it there, but none of these softwares you work that so far. Either you have a structure that they will still use in secondary gradient calculation and calculate this way. But in your own codes, you have some structured mesh for 3-dimensional. If you are 2-dimensional structured or unstructured, it is good that you start with previous methods that we have discussed. So you can calculate the total value, subtract the primary gradients to get the secondary gradient. This is how all these commercial ones use and open source ones work. For the calculation of the gradient on a particular phase, for calculating grad phi. So grad phi can be taken as the average value of this grad phi which we are going to calculate. This can be taken as average value of all the cells and the total values that you take from grad phi naught plus grad phi 1 by 2. So that means you calculate the gradients of phi at the cell centroids itself and store them. And if you want at the faces, you linearly interpolate how it works, how this works basically. Grad phi can be computed. Grad of phi at that phase can be computed as grad of phi at that cell centroid phi naught, C naught, then 1 divided by 2. Okay. So now this we will see in the coming lectures that how to calculate the gradients or it. Okay. So let us say we have a linear problem. Now we come up with the linear problem of the source terms. We have so like we had a constant source term, but when we are working on a steady diffusion in 3-dimensional with constant source and constant gamma, if we have using the non-orthogonal mesh, what modifications can be required? Okay. For steady diffusion, orthogonal and non-orthogonal kind of meshes. All right. So let us proceed further. That is steady diffusion on non-orthogonal meshes. Correct. There will be some source terms. So, unstructured non-orthogonal meshes. So the equation we have a kind of derived is basically summation of f gamma grad phi at the base dot af plus the source term s bar which we used to write is p phi p. So del v naught phi naught, right? Equal to 0. Okay. Now we are working with a diffusion flux term. AF have some quantity that has phi zeta, that is the gradient in the z direction, plus some other quantities with eta. So now that we say like we have a we said it's of course the derivative in the z direction can be written in the terms of cell values using the linear profile assumptions. If I minus phi naught by del zeta and so on. for the primary gradient, and the second term we say that it is a secondary gradient. We got these two terms so far. We have devoted a lot of time for calculation of like primary and secondary gradient. All right. We have seen that gamma grad phi at phase dot AF was having primary gradient plus secondary gradient. Primary gradient has linear interpolation. Now, if we say secondary gradient can be computed as total minus primary gradient, which we have just done. All right. A question came that how you will calculate the grad of that. Secondary gradient can be written as total minus primary gradient. We know the equation in terms of grad of phi, something grad of phi, right? In terms of grad of phi. Correct. How you will calculate thing. So he said that we don't know the phi value itself. They are the unknowns. But now we are talking about the calculating the value of gradient of phi's, which needs to be somehow computed on the face, right? So now the calculation of secondary gradient is reduced to the problem of calculation of gradient of phi. Earlier we used to have secondary gradient of phi. In the secondary gradient, we used to have dou phi by dou zeta. And now it is reduced to grad of phi on the face. So if we can calculate the gradient of the phi on that face, we can calculate the secondary gradients. So again, we say that using the approximation, if we have the gradient of phi, it can be assumed to be constant in a cell. If it can be assumed to be constant in any cell, then the gradient on the face can be written as an arithmetic mean of the gradients of the cell values. Okay. So what do I mean? Grad of phi can be written as grad of phi naught plus grad of phi 1 by 2. The same. Okay. And we average these values to get the value at the face, grad of phi. That's it. So why we chose the arithmetic mean? So essentially we have two cells and the gradient is assumed to be constant over these entire cells. So then the face value can be taken as the arithmetic of these two. And even if it is not equal to grad of phi, then grad of phi is assumed to be constant over the entire cell. So whatever is the distance between these two cells doesn't make a difference. For example, I have these two. Right. So this was C naught, this was C1. I don't bother about whatever distance is there. It doesn't make a difference. So if there is a variation of grad of phi inside for a particular cell, the grad of phi is constant in this cell, grad of phi is constant in this cell. Okay. And the mean of both of them can be taken out of it. So wherever I go, whether I go outside of the cell, it will be having the same value in corresponding to that cell for that particular cell entirely. And if it is not constant, then of course, then you have to take some linearly independent values. Another question can be like the concept of coming off the gradient of phi calculations came from the motivation of the secondary gradients only. Calculation of the secondary gradients which we have. So now if you have a non-orthogonal mesh, suppose your cell is looking something like this. Okay. Yeah, C naught here. Here it is C1. Here it is C2. Here it is C3. Okay. These are the phase connecting. Suppose this is phase 1, phase 2, this is your phase 3. All right. So what I'm saying, sir, discrete equation for non-orthogonal. So let us assume all these and write the discrete equation for the non-orthogonal meshes. So until like before, we have been talking about, let's say there is one phase F here, but actually if you would have several phases connecting to one of that, connecting to several cells, you will have another cell. So we have suppose C naught is covered with 3 different cells. So there are 3 different phases F1, F2, F3. All right. So you have a summation, you have to do the summation of grad of pi's of all the cells. And if we write similar equations for each of the phases and then kind of assemble them, so considering all these phases F for that particular cell C naught, we would write the equation for the cell C naught in a way AP5P AP5P is equal to summation of A and B phi and B plus P. A and B phi and B plus B. So if where A and B's are the coefficient for the neighboring values, so you will get the primary gradient again and secondary gradients. Where A and B is nothing but gamma F, F, AF dot AF, AF dot E theta. All right. So this phi P, if we say it is nothing but for cell C naught, so AP phi naught. Right? And this is your A and B. So AP can be written as neighboring A and B minus your source SP delta V naught. And B, the constant term can be written as SP delta V naught plus neighboring cells secondary gradient as well. So similar in structure to an orthogonal systems. So you know what is primary gradient, you know secondary gradient. You can take out the secondary gradient from total minus primary gradient. And let me write here. Similar in structure to orthogonal system. A and B are the coefficients from the neighboring cell. So will it be coming from the primary gradient? Whatever is the primary gradient, that is gamma F upon this entire term, whatever I've written. Okay. So which was gamma F by phi of zeta into AF dot, sorry, del of zeta into AF dot upon AF dot E zeta into phi 1 minus phi naught by linear interpolation. This means that what is the coefficient here is the entire term is in the parenthesis of this equation. If I write the equation, gamma grad of phi of F dot AF is some equation here into phi 1 minus phi naught upon del zeta. This was your primary plus something here for the secondary term, phi of beta, that phase. This was your secondary. Okay. So this term was having some value uh, that was like this. Okay, and this will be your coefficient. Okay, this will be your coefficient. And if you say in the absence of source terms, in absence source terms, your S will be 0, S bar, sorry. So AP can be written as summation of A and B minus, okay, only summation of A and B. No other thing is there. So in the absence of source term, your S bar is 0, A summation is this, but and Scarborough criteria is satisfied. But what about the bondedness? Uh, Boundedness, that means you have source equal to 0 for this case. So essentially source is 0. So this term is AP phi naught is equal to summation of A naught, the summation of A and B phi and B plus B. There is some B which is having some secondary terms. Okay. What do I say? This satisfies Scarborough. In the absence of source, your for the boundedness, your phi naught is nothing but summation of A and B phi and B, that's B over AP. And this is not 0, even source is 0, because secondary gradient is present. The boundedness is not assured. Therefore, you can say, right, that means secondary gradient term will create some oscillations in the solution. It will create some oscillations in the solution. Okay. Now, if you have a boundary flux calculations, coming to the boundary part, so far we were dealing with internal cells. There is some boundary flux calculation. The cell is at the boundary. So this is your cell, and this is your boundary. And this is still centroid C naught here. It doesn't have a neighboring in this direction and this direction because it's a boundary itself. That means it's phi naught here. Okay. And this part is connected to internal cell. This part is connected to the internal cell. Okay. This is your A boundary. Okay. A of the boundary. So suppose this is connected with this here boundary. This is again non-orthogonal E theta hat, and this is E eta hat. Okay. Angle is greater than 90. So at the boundary here, phi is equal to 5, sorry, phi A and phi B not phi B are known, right? Phi and phi B are known. This is how much? Zeta direction, that means del zeta. When you write the discrete equation for this, how you will write? You will have internal faces connected to internal cells as well as the boundary cell. If I write for the internal cell, summation of internal cell gamma dot phi f dot AF plus now we will come along with neighboring cell, or sorry, boundary cell, phi of boundary dot A of boundary plus if you have some source term SCSP phi naught del V naught is equal to 0. Again, now you have done for all this. Now time is to see for the boundary part. So this can be written as gamma B AB AB. Earlier we used to write AFEF AB dot E of zeta into phi of zeta at boundary as zeta at the boundary. All right. How you will write the phi of zeta at boundary now? Phi of zeta at boundary can be written as directly you will not be able to do the linear interpolation because there is no east space for this. So you'll write boundary minus del naught, which you used to do similar way, and this is del zeta boundary. This is del zeta boundary. Okay. We used to do del x by 2 there. So again, we have primary gradient, secondary gradient. We can make 2D structured, unstructured, 3D structured, unstructured. Okay. All right. Similar kind of thing. So your primary gradient looks like something like this for the boundary. Will be gamma b over del zeta b into ab dot over ab dot e zeta into phi b minus phi naught, right? And this will be a coefficient ab. So here you know phi b at the boundary, but the question is you don't know this, right? So either you can apply the Dirichlet or Neumann or mixed kind of boundary conditions to solve it. That's all upon you. So we have written the primary gradient. So the burden is more on the interior spaces, right? So if it's a structure, it's a 2D mesh, we can somehow calculate phi of the neighboring cells along the tangent. If it's a 3D structure, we can somehow calculate it. But if it's a 3D structure, then we have to do the business of calculating the total values minus subtracting the primary gradient for unstructured, right? But structure we used to do. So for 2D structure or unstructured, it can be calculated using the interpolation. For 3D structured, it can be calculated. At 3D unstructured, we do not have a unique way of defining the two secondary gradients for zeta, eta and psi directions. Okay, all right. So you can either apply Dirichlet, Neumann, or mixed boundary conditions. Okay, kind of boundary conditions you can use to solve and discretize the equations. And again, you can have a source or no source depending on what kind of situation you're dealing with. So if you are dealing here with the absence of source, so let me write the equation. Your equation is AP phi naught is equal to summation of A and B, phi and B plus B. Okay, where A and B for internal phases, you know, this A and B is gamma F, psi F, AF dot AF, AF dot E zeta. Okay, where you have all the internal phases. So your AP will be summation of A and B plus AB minus SP del V naught. Okay, and B will be SP del V naught plus SG of the internal secondary gradient factor plus AB phi B. You have the boundary nodes plus secondary gradient of the boundary. Okay, so secondary gradient of the boundary. All right. So here two loops will run. Secondary gradient for internal loop and for the internal for the boundary as well. So two loops for the boundary for the internal part. Two loops are there. All right. Any doubts in here? So suppose in the absence of source, if you write, that means your S will be 0. Okay. So that means your AP will be, this AP will be greater than summation of A and B's. Satisfy the Scarborough inequality, but boundedness phi naught is not assured to be bounded by cell neighbors. Again, it has some secondary gradient values again here. Okay. Scarborough satisfies in inequality. Boundedness not guaranteed. Okay. As phi b is not assumed to be bounded by the neighbors. And you can extend all this to if you have gamma which is not constant, you can interpolate. You can extend to unsteady. So you can have linear source terms, linearization of the source term. You can go with the under relaxation. You can do the stability anything. You can deal with Neumann boundary condition, mixed kind of boundary condition, and so on. All right. So I guess this is for the tutorial for today. I hope there are no doubts. Just be regular to the tutorials. Very important. Complete your assignments. You will understand everything. And just write down by your hand as well all these things. All right, we can end the session. We can leave. Thank you for joining.